Please, Yue, the floor is yours.
Okay, nice. So hello, everyone. I'm very glad to be here to present my current work, which is a B-objective electric autonomous dial-ride problem. This work is collaborated with Jacob, Sophie, and Nicola. And today's presentation, I will first give you a brief introduction on the problem and the background and the motivation. Then in the second part, I will present different methods to solve the problem. And the third part are the ongoing results and the discussions of results. And my presentation will end with conclusions and the next step of my study. So now let's begin with the introduction part. A series of transport-related problems such as greenhouse gas emission and urban traffic congestion have appeared in the worldwide. Those problems have severely impacted both environment and economy and has become huge challenges for human societies nowadays. To handle those problems, three possible directions have been proposed. The first is to use electric vehicles. It has the advantages of potentially producing fewer greenhouse gas emission and lower noise. Another direction is to develop autonomous driving technology, and the introduction of autonomous driving in managing the vehicle fleets allows to have more flexibility, and it can help to lower down the operational cost and provide better service quality. And the last possible direction is to provide ride-sharing services. And the underlying optimization problem is usually modeled as a dial-ride problem. And those three possible directions compose the topic of my presentation today. That is electric autonomous dial-ride problem. Let's call it EADARP. The EADARP was initially introduced in 2019, where it consists in scheduling a fleet of electric autonomous vehicles to provide ride-sharing services to a set of customer requests. And to illustrate, I will give you an example. Here in this slide, there are two vehicles, and normally there are four kinds of nodes that contains in the EADARP. The first is the set of original depots that each vehicle must start at. And second is the destination depot set, where each vehicle must end their trips at. And the third node set are the customer nodes, which include pickup nodes and drop-off nodes. To distinguish, I marked here different requests in different colors. So there are four customer requests considered in this example. And each customer request contains a pickup node and a drop-off node. And the last node set is the set of recharging stations. So imagine that we consider the minimization of operational costs as our objective function. Then we will have this operational optimal solution. However, we found that in the first route of this solution, the vehicles travels from depot and passing through two customer requests, and the passengers related to request 1 share their ride with passengers related to request 2, so that the passengers of request 1 are not traveled directly from their origin to their destination. This indicates that the passengers of request 1 has an increased total user ride time. To conclude, this solution is operational optimal, but it is not service optimal. And how about if we consider the minimization of total user ride time as our objective and try to provide the best service quality? Then we will have this service optimal solution. And in this service optimal solution, each request is transported directly from its pickup to the drop-off. Then we have this solution has a minimal total user ride time. However, from the perspective of operators, this solution is not good because we notice there is a significant increase on the total travel time and also an increased battery consumption. To conclude, this solution is service optimal, but is not operational optimal. And from these two examples, we find a conflict interest between the operators and users. So the motivation of our study is that we want to provide a full picture to analyze the trade-off between the operational cost and service quality. And we want to strike a balance between those two factors. This is our motivation. And the B objective EADARP, in the B objective EADARP, we consider the total travel time as our first objective. And we also take into account the service quality as our second objective, which is formulated as the total access user write time for all the user requests. And the access user write time for our user request is calculated as the difference between the actual user write time and the direct travel time. And for this point, I will give you an example to illustrate the access user write time calculation. Here below is a partial path that the vehicle starts from the original depot, passing through two customer requests, the request 1 and request 2. And here, upon the dashed line, I also show the direct travel time from the pickup node 1 plus to its drop-off node 1 minus, which is equal to 16. And here in the table, I present a feasible schedule denoted as schedule 1, where I present the service start time at each node along the partial path. So the actual user write time for request 1 is calculated as the difference between the service start time at its drop-off node and the service start time at its pickup node, and it is equal to 17. And the direct travel time is equal to 16. So the access user write time for request 1 is equal to 10. And similarly, we can have the access user write time for request 2, which is equal to 5. So with schedule 1, the total access user write time for this partial path is equal to 15. And before I present the methodology, here are some basic notions. The main goal of our study is to calculate the Pareto optimal solutions, which is also called efficient solutions. So what is efficient solution? A feasible solution is called efficient if there doesn't exist any other feasible solutions that weakly dominate it. And its image in the objective space is called non-dominated points. And for a B-objective problem, its objective space is a bidimensional area as shown in this figure. And in our case, we denote Z1 axis to present the total travel time of a solution, and Z2 axis to denote the total access user write time of the solution. So consider a feasible solution X. Its total travel time is denoted as Z1X, and Z2X is the total access user write time of this feasible solution. So each feasible solution, its image in the objective space is actually a point that's coordinated by its first objective function and the second objective function. As I showed in this figure, the image corresponding to solution X1 is coordinated by Z1X1 and Z2X1. And here, all the red points are the non-dominated points, because we cannot find any other points that's dominated. And now I will present the methodology to solve the problem. We have considered different methods to solve the B-objective EADAR. First, we consider the epsilon constraint method, which is widely used, and it is kind of objective space search algorithm. And second, we proposed a generalized branch and price algorithm, which we called it BOBP algorithm. Then I will present the idea of each kind of algorithm in the following slides. The main idea of epsilon constraint method is that we first solve two lexicographical optimization problems, and we obtain two non-dominated points denoted as ZT and ZB in this figure. ZT is obtained by first minimizing the total travel time. Then, among those solutions that has the minimal total travel time, we select the solution that has the minimal access user write time. Then we obtain the Z1, the ZT point. And similarly, we can obtain the point ZB. With those 2 points, we can define a rectangle area, which includes all the possible non-dominated points. And also, ZT provides the maximum value on the total access user write time, which is denoted as epsilon. Then this epsilon value is used to define a problem where we put one where we put one objective in the objective function and the other objective is in the constraint and bounded by the epsilon value. Then we solve this mixed integer problem and we obtain the next non-dominated point as shown in the figure, the red point. And the epsilon value is decreased to epsilon 1. Then the mixed integer problem is reformulated with this new epsilon value and we solve again. And by repeating the above process, we can obtain all the non-dominated points. However, this method has a drawback. The main drawback is that each time we solve a mixed integer problem and it's too hard in practice. So this drawback inspires us to consider another algorithm that is based on the idea of branch and bound, that is the BOBP algorithm proposed in our study. And the idea of branch and bound is divide to conquer. That is, we divide the original problem to simpler subproblems, and we conquer each subproblems in order to find the global optimal integer solution. However, there are two main challenges in the branch and bound to tackle the B objective case. First is the bound computation. In the single objective case, each node is only associated to one linearized problem. So we just need to obtain the optimal solution for this problem, which is just a single numerical value as shown in the figure left-hand side. However, in the B objective case, the solving process of each node of the branch and bound tree associated to obtain all the non-dominated points. That is, we need to calculate a set of bounds instead of a single numerical value. And the different computation process of the bound set result in different fastening process. And in the single objective case, a node of the branch and bound tree can be either fastened or not fastened. However, in the B objective case, a node can be just partially fastened. Here I show a small example where the blue points are the bound sets that we calculated at the current node, and the red points are all the points that corresponding to integer solutions that we calculated through the tree search. And those red points are usually called the upper bound set. So in this case, the blue point set are just partially dominated by those red point set. So we cannot fasten the node in this case because the non-dominated search area may contain new non-dominated points. And now in the following slides, I will present how we handle the bound computation and fastening in the BOBP algorithm. There is one problem of computing the lower bound set in the B objective case at our node, because at each node on the branch and bound tree, we actually solve the linearized B objective problem, so that we cannot compute all the non-dominated points, assuming that x1 and x2 are two feasible solutions. Their linear combination is also a feasible solution. This indicates that the non-dominated points is actually located on the line that's connecting the extreme points, for example, x1 and x2, as shown here with the triangle. So in this case, we may have infinite non-dominated points, and we cannot compute all of them. And instead, we consider to compute all the extreme points as our lower bound set. That is all the green points here, and those green points can be computed by applying dichotomic method. And I will not precise the dichotomic method in my presentation. So after we computing the lower bound set with the dichotomic method, we must evaluate this node and decide whether it can be fastened or it's just partially fastened. So assuming that the lower bound set computing from applying dichotomic method contains three extreme points, that is P, Q, and V. And then we introduce the local nadir point to define the search area, which may contain new dominated points. So the local nadir points is coordinated with the maximum possible value on both objective, which is denoted here as C1 and C2. So the green area here is the search area that may contain future non-dominated points. Then we split this search area by introducing the lower bound segment, and each lower bound segment is considered as a research area that is defined by two consecutive extreme points and a local nadir. So this green area can be partitioned into these two small area, which we call each area a lower bound segment. So the first segment, lower bound segment, is defined by the extreme points P and Q as the local nadir point C, and the second lower bound segment is defined by extreme points Q and Z and local nadir point C. So it is shown in the light yellow area here. And then we evaluate each segment with every point in the upper bound set. Note that the upper bound set presents all the integer solutions that we obtain through the tree search. And there are 4 cases might happen when we evaluate a lower bound segment. And I will present each of the cases in the following slides. In the first case, the point in the upper bound set is located on the left up side of the segment. Then this point can help to reduce the search area from the local nadir point C to C prime. Then the segment is updated to PQC prime. Similarly, when the blue point is located in the right down side of the segment, then we can also use this blue point to reduce the search area to the segment defined by PQ and C prime. So from after the filtering, we update the segment to PQ and C prime. And for the second case, it's more complicated because the point is located upon the line that connecting the extreme points P and Q. And in this case, the original segment can be split into two smaller segments. That is segment 1 denoted by P, U prime, and C prime, and segment 2 denoted by the U prime, Q, and C double prime. And similarly, in this case, the blue point is located upon the line that connecting P and Q, and it can also we can also obtain two smaller segments after the filtering. That is segment 1 and segment 2 represented in the blue area here. And now I will present a complete filtering process of lower bound set by the current upper bound set. So here in these figures are the black points represent the points in the lower bound set that we calculated after applying dichotomic method. And the blue points here are the points in the upper bound set that's corresponding to the integer solution we obtained through the tree search. So here the blue area represents the first lower bound segment composed by the two extreme points and the local nadir point. So we filter this segment with the first blue point. Then we can obtain two smaller segments represented in the smaller blue area, and then we move to we continue to evaluate those two segments with the next blue point. Then we obtain a smaller segment, and for the third blue point, it has no impact on the segment. Then the filtering process for the first segment is finished. And we repeat the above process for the second segment, and we obtain the pink area. And for the third segment, we obtain the green area. And for the last segment, we obtain the yellow area. And all those areas may contain the non-dominated points. And then we will consider the branching on each of those areas, and I will not precise it in my presentation. And now I will present the ongoing results with applying different methods to solve the problem. In our study, we have tested our algorithm on 18 instances, with instance of 4 vehicles and 26 requests. The time limit to solve each request is set to 5 hours. And here is the aggregated results on different algorithms. And and we report the average CPU time and the average CPU time the CPU time for computing each instance, and the average CPU time for obtaining each efficient solutions, and the numbers of efficient solutions that we obtained by applying different algorithms. And we found that our proposed BOBP algorithm outperforms the epsilon constraint methods because we can say it generates more efficient solutions and it spends less time on each instance. And here I present in the left-hand side the figure which contains all the non-dominated points that we obtained for an instance. And the x-axis presents the total travel time, and the y-axis presents the total access user write time. And we found that the points in the red rectangle, that those 2 points corresponding to 2 efficient solutions that has almost the same values of total travel time. And however, they have a huge difference on their access user write time. It gives us the insight that that we can reduce significantly the access user write time with only a very, very small increase on the total travel time. Those solutions are very interesting for the profitable companies such as Uber and Didi, because they can use the solution to largely improve their service quality without a huge increase on their operational cost. And also, we found these 2 solutions in the 2 points in the blue rectangle, that those 2 points are corresponding to the efficient solution that has almost the same level of the access user write time. However, there are huge difference on the total travel time. So it gives us the insight that the operational costs can also be reduced without degrading the service quality. So those solutions are very interesting for the non-fitable associations like the Red Cross, because they can use those solutions to decrease their operational costs while without degrading their service quality. And now I will conclude the presentation and illustrate the next step for my research. So in this study, we have proposed a BOBP algorithm that is more efficient than the classical epsilon constraint method, and is generate more efficient solutions in less average computational time. And the obtained efficient solutions offer managerial insights for different service providers. Those solutions can also help them to select path-optimal transportation plans according to their priorities and preference. And for the next step of my study, I will further enhance the computational efficiency of the proposed BOBP algorithm. And first, I will develop methods that can efficiently check the existence of the non-dominated points in a given search area. And the second direction might be to add cat to enhance the lower bound set so that the number of nodes in the BOBjective branch and price tree is reduced. And there are the references and the acknowledgement. Thank you very much. And if you have any questions, don't hesitate.
Thank you very much, Yue, for your nice presentation. So are there questions or comments? Flo, go ahead. I will turn off the...
Oh, okay, yeah, recording.